We're all familiar with different types of materials having different electrical properties. For example, the plastic around this wire is an insulator. The copper is a conductor. This transistor contains silicon, which is a semiconductor. And then, of course, there are magnets, typically made of iron. And you may have also heard of superconductors. Certain materials offer no electrical resistance at all when they're cooled to incredibly low temperatures. Well, imagine this. When I first found out about it, it blew my mind. Imagine you could take the same material and completely change its properties at will. So it could be a conductor, an insulator, a semiconductor, a magnet, even a superconductor. Well, that possibility is now one step closer to reality. To understand how that's possible, there are two things you need to know about. The first is graphene, a special form of carbon that exists as a two-dimensional sheet. It's a single layer of carbon atoms arranged in repeating hexagons. Now, hold that thought because I want to introduce you to something called moire patterning. This is something you can try at home. Take a sheet of paper covered in tiny hexagons, and then a transparent sheet with exactly the same pattern on it and lay it on top. When they're perfectly aligned, you just see a regular grid. But if you rotate the top sheet, you start to see strange, beautiful patterns appearing. This is moire patterning. But what has this got to do with those magical properties I described earlier? It turns out that if you stack two sheets of graphene and slowly rotate one relative to the other, the electrical properties of the combined sheets change quite dramatically. So why does twisting a sheet of graphene relative to another do this? It's all to do with the angle between them. This so-called twist angle changes the pattern that we see. But in graphene, this twist angle changes the way the electrons in the graphene move and behave. Normally, the electrons form a whizzing cloud between layers, but the twist changes this. And what really changed the game was the discovery of a so-called magic angle of precisely 1.1 degrees. At this angle, the electrons across the graphene sheets effectively stop moving and begin acting as a coordinated unit. This is where the magic really happens. The electrons are locked together in what's called a flat band, and this allows us to manipulate their electrical properties. So, for instance, applying and changing a tiny voltage across the graphene sheets can turn them into an insulator or a superconductor. It can turn them from a magnetic to a non-magnetic state. This is extraordinary because instead of going through the laborious process of engineering different materials to do different jobs, you can have one material that does all of them. And this means in years to come, we could see a new generation of low-power electronic components, far more precise sensing devices, and even a new generation of quantum computers. One day, it could even help us build room temperature superconductors. The sky really is the limit. And because this new field promises a new kind of electronics based on the twist angle between the two sheets, it's been given the name Twistronics.